Reading week 12. This week's main physics idea was RL circuits and Gauss's law. We first looked at a solenoid circuit where it had a solenoid connected to EMF of a battery, and we learned that it causes self-inductance, which basically means it is inducing current within itself. And from this, we found out the EMF of the solenoid equals to the number of loops times the d flux over dt. And this equals to L, which is the inductance, times di over dt because current is changing as time changes. And from this, we led to the loop rule of EMF of battery minus the EMF of solenoid being equal to 0. And then we looked at resistor-inductor circuits. And from this, we looked at the instantaneous time where the current is increasing from 0 to a value of EMF over R. And so we calculated this value by looking at a series circuit with resistor and an inductor in series. And then we used the loop rule to find I sub t, which is current. And that was equal to be EMF over R times 1 minus e to the power of negative t times R over L. And this basically means when time starts from 0 to certain t, we know it is going to have a significant value at t equals L over R because that's the time constant, and eventually the current is going to reach EMF over R. And lastly, we looked at Gauss's law for electric and magnetic fields. For electric field, we know the equation equals to integral of E field times the normal vector times dA, and this is set to equal to the charge enclosed inside the closed surface over epsilon sub 0, which is basically a constant. And for magnetic fields, we know the integral of B field times the normal vector times dA is equal to B0. What I already knew from the previous weeks was the idea of induced current and loop rule. And what I did not already know was through the evaluation of different circuits, like the solenoid circuit and the resistor-inductor circuit, we can find different rules, and that the integral of closed surface is used to represent the symbol for Gauss's law, which is an integral symbol with a circle in the middle. And on the right, figure A shows an example of the resistor-inductor circuit, and on B, as you can see, it shows the time graph as t increases with I, and this shows when t goes to L over R, there is a significant change in current. Something interesting that I learned was that the solenoid circuit not only induces the loop nearby, but also itself. And this week's idea related to my major in terms of electrical engineering, because a resistor-inductor circuit refers to a circuit having combination of resistance and inductors, and this is commonly used in chokes of luminescent tubes. A confusing topic for me was how to derive the Gauss's law for electric fields. I wasn't sure if you can just say that the charge inside the closed surface can be found using the equation given, or it's derived from the original equation. And as you can see from this internet search that I've done, you can find the change in flux using the equation E times the normal unit vector times dA, and you can derive it using the equation 1 over 4 pi epsilon times q over r squared times r unit vector to represent the E field. And from this, you can find the net flux by integrating this flux over the surface of the sphere, and this results in Q over epsilon 0, which basically is the equation that we use to represent Gauss's law for electric fields.